Welcome everybody. I'm very happy to open this event. I am Mariapina Limongelli, Associate Professor of Seismic and Structural Engineering at Politecnico di Milano in Italy.
And I'm Salvatore Di Bernardo from a consulting engineering firm, Siorba Group, based in the United States.
There will be a short introduction of IABSE to open the webinar and a description of the duo webinar. And then we will leave the floor to our two speakers today, Professor Costantino and Dr. Zhu. I leave the floor to Salvatore, who will present IABSE, but I will show my screen.
So I would say a few things about the IABSE, International Association for Bridge and Structural Engineering. The name, I'm hoping that a lot of people are members, but I'm also hoping that we have non-members that will consider knowing more about our association. You can go to the next one. The mission of IABSE is to exchange knowledge and advance the practice of structural engineering worldwide. And this is a good example. Today's event is a good example of what we do. One of the thing that defines us is the international participation. So we have like 100 countries represented in IABSE with over 2,500 members. Some of the highlights of what IABSE does, there are several publications that are managed by the association, a journal, bulletins, and conference proceedings. Conferences are the most important events that we do. Things have been changing lately, and we do more online-based event like this one. The association is organizing national groups and task groups. So pretty much all the 100 countries have like national groups. Some of them do some joint activities, and we try like at the local basis to be very active with our community. These are like highlights of some of the most recent events. So you can see that there is a lot of activity worldwide. And then technical commissions and task groups are the core of the association, in which there is research, exchange of ideas and scientific contribution along the tasks that you see listed here. We have like 6 technical commissions and 45 task groups. Talking about like future events, as of now we have like the next one will be like an in-person event, will be Prague in May, in a few days. And then the next major event will be the Congress in Nanjing in September of 2020, this year. So, and then we have a very strong young engineer program. We encourage younger people and students to join the association and appreciate the value of what we do from a technical point of view and academic point of view. Thanks. You want to say something about Commission 1?
Yes, this event is organized by Task Group 1.9, which is one of the task groups of Commission 1, which deals on performance and requirements. And there are 9 task groups, as you can see here. And the dissemination of which this webinar is a part is in charge of Task Group 1.9. Specifically, this event is one of the duo IABSE webinars that are events that aim to provide a forum to present and discuss hot topics related to bridges and structural engineering, which is the focus of IABSE. And this particular format is based on a discussion between an academic, and today we have Professor Costantino, and the practitioner, and we have Dr. Zhu, who bring different perspective, and this makes usually a very lively discussion. At the end, also the participants to the event can integrate the discussion. There will be a Q&A session at the end, and you can post a question in the Q&A during the event. We will read them and ask the question to the presenters. Specifically, this event today is on seismic isolation, as you already know, of course, and the two speakers will talk about concepts, research, and outstanding applications. And the content, let's say, one of the focus of the event will be the description of the Beijing Daxing International Airport, which was recently awarded as outstanding structure by IABSE. And here you see some of the topics that will be tackled by the two presentations, but there will be even more with respect to this. Very important point, the presentation after the event will be uploaded on the IABSE e-learning page. If you don't know, it's important, it's an interesting point. IABSE has an e-learning page where you can find videos of webinars like this and much more. And also the webinar will be telecasted live in Facebook. We have a sponsor, Seismic PS. Seismic PS is dedicated to the development and application of advanced seismic protection technologies, and you will see more now in a video of our sponsor. Maybe Firat can help with this. So, okay.
So, Maria Pina, I
Yeah.
can
Sorry,
chime in.
I take some time to share the screen again. Now Salvatore will present our speakers.
Yep. So we are ready to go, and I want to my pleasure is to introduce Professor Costantino, who is the first speaker of today's presentation. Professor Costantino is the Samuel Capen Professor and also a State University of New York Distinguished Professor. He's at the University of Buffalo, New York. He's the editor of the Journal of Earthquake Engineering and Structural Dynamics, the recipient of the 2015 ASCE Newmark Medal, which is a very highly regarded award. And he's been, during his career, he's been focused on seismic protective system, earthquake engineering. He has published over like 300 papers. He's been involved also on the private side doing consulting work or peer review for like several projects worldwide. So it's an honor and a pleasure to have Professor Constantinos with us today, and he will be a source of great information about earthquake protection and seismic isolation of buildings and other structures. So without further ado, I think we are ready for you, Professor Constantino.
Well, thank you for the introduction, and I'm very pleased and honored to participate in this event. Let me start. Okay. Can you see the screen properly?
Yes, very well.
Very well.
Because I have, okay. Well, the presentation is on seismic isolation, an overview of concepts, implementation, and related research. Of the many seismic protective systems you're aware of, I will concentrate only on seismic isolation, and for that only for specific systems that have found widespread application, and including some with viscous dampers in them. So we have elements of passive damping, but I'm not going to talk about other things, that are so many. So I will go over a description brief of seismic isolation principles and its most widely used systems, some implementations in buildings and the infrastructure. Actually, I will show a couple of bridges since the IABSE has something to do with bridges, some research results that are of significance related to seismic isolation systems. Since I'm making the presentation, I will put emphasis on work that was done at the University of Buffalo, and I will show projects in which I was involved. I cannot talk about what others have done, but the scope at the end is to demonstrate the maturity of the technology and the range of its application. And I want to acknowledge many of my colleagues and sponsors. Since this presentation will be available, I will make a version of this available to all participants after the seminar. Therefore, I'm not going to dwell on some of the details of the slides or going over each individual person contribution in this slide. Now, seismic isolation is a method of construction and a technology in which a system is used to provide period lengthening and ability to dissipate, absorb energy, characterized by flexibility of the isolators, results in force, acceleration, reduction, and as a result of that, increasing displacements, which are concentrated in the isolation system with small structural drift. I will be talking about isolator displacements of the order of 500 to 1,000 and even more than that millimeters, so 1 meter of displacements, hence the need for damping. And I will elaborate a little bit why we're talking, or at least in the United States and the projects I was involved, about 1,000 millimeters plus of displacement capacities for the isolators. In typical analysis of isolated structures, you're going to use 7, nowadays 11, but let's say 7 to 11 ground motions, triplets, that's X, Y, and vertical, to estimate isolator displacements. They are good at estimating median or average values, but uncertainty in the response and requirements that you have acceptable collapse risk determining the displacement capacity of the isolators. As an example, I take this case in which analysis gave a displacement demand in a median sense of 350 millimeters, but the displacement capacity of the isolator is provided as 700 millimeters, twice as much. There is something related to this, in an application, and that is actually in one of offshore platforms. You are going to see images of that in Sakhalin in Russia. Now, if the uncertainty is quantified by the dispersion in a normal distribution. And we assume the dispersion to be 0.3, which is rather low. It's more characteristic of motions, ground motions in California. The probability of exceeding the 700 millimeter capacity is 1%, which is pretty low. But if the dispersion is 0.7, then the probability of exceeding that is 16%, which is unacceptable. So the isolator has to be made even bigger to have acceptable collapse performance. And dispersions of this order are characteristics of motions, because uncertainty in the ground motion drives everything. Are characteristics of motions in, let's say, South America, in the northwestern United States and Canada, in Japan, for example. Now, of the isolators I will discuss something about are lead rubber isolators, friction pendulum type of isolators. We have several versions of those, and viscous dampers. I will start with this, a very good example of a hospital in Turkey built, completed some 15 years ago. And to get an idea, of the isolators in this case, they are almost 1.2 meters in diameter, and they have a displacement capacity well above 500 millimeters. 500 millimeters is the displacement computed in an average sense in the maximum earthquake. So there are about 400 isolators, actually 386, and there's a mixture of lead rubber and rubber isolators. A characteristic of these isolators, lead rubber, which is a very successful system, is ability to dissipate energy. And you can see this with this force displacement loop in the horizontal direction, of course, that indicates a large ability to dissipate energy. The area enclosed by the loop is significant. I will point the strength as being about 10% of the weight carried by this isolator. And you can see, very important, that it changes from cycle to cycle as a result of heating effects, which need to be quantified, in testing. And this particular result is from prototype testing of the isolators for that project. The temperature of the bearing affects the behavior of the bearing, not only in terms of the heating effects, but also in terms of a direct effect on stiffness and strength, as we look at effects for a bridge in bearings used in a bridge in the United States, actually in the state of New York. You can see approximately a 65% increase in the strength of the bearings when we look at the effect of temperatures between 20 degrees and minus 26 degrees Celsius over a period of 2 days. Now, the exposure time is very important and depends, of course, the effects depend on the size of the isolator. For example, these were small isolators for a bridge because the displacement demands were small. This is in the state of New York. But if these were somewhere in Canada, it may have been prohibitive actually to use the isolators because the exposure of, to low temperatures is significantly longer, resulting in more effects of the low temperatures. The effect of the temperature can be understood by looking at the force stress strain curves, of lead. In this case is pure lead in tension under some kind of dynamic conditions, actually, that this type of results are used to develop models that predict the behavior of these bearings. Switching now to friction pendulum bearings, we start with a single surface friction pendulum isolator. This is an image from our lab in 1988. And actually this particular isolator you see now open, I have it here in front of me in the office, still functional. And this is one of the largest ever made isolators. I will point to this 700 millimeter displacement capacity, having in mind what I earlier mentioned about the why these displacement capacities are so large. This isolator carries a gravity load in one of the applications that is just over 10,000 tons. That's per bearing, and including the vertical ground motion effect, 13,000 tons, which is exceptionally large. And one may wonder, how can someone test an isolator like this? Well, I mean, you cannot test it at full scale dynamically, so something else has to be done. To give you an idea why something like this was used, an isolator like that was used in that platform that weighs about 40,000 tons. These are two of those platforms, and it can give you an idea of what exactly, and you can see the weights of these two. But there's a third one, which is heavier even. And understand the effects of the various loadings that one has to consider, from temperatures, low particularly, to snow, which is exceptionally high. Snow and ice accumulation is much more than anywhere we design, for example, in the United States, except up on the mountains of the Western United States. But most important is actually sea ice. To give you an idea of the effect of that, the 1 year return period force on each leg of the platform, and there are 4 legs, is 100 and a little bit meganewtons, so 10,000 tons, which is actually more than the gravity load. So isolation, seismic isolation, is not used to protect the substructure, the gravity, concrete gravity base, but actually to reduce accelerations in the secondary equipment in the structure above. And to give you an idea of that, in low-level earthquake, for which the facility must remain operational, you can see reductions of accelerations that are significant by a factor of approximately 2. Is not 10 that some studies, show, coming typically out of universities, but is significant enough to consider seismic isolation. There are also other effects, like allowing for thermal expansion and contraction and reduction of the stresses. You have to realize that this is 100 meter by 100 meters expansion and contraction from minus about 40 to plus 40 degrees Celsius have significant effects that are mitigated.
I think we're having some technical issues with Professor Costantino.
That follow these isolators are at load of 10,000 tons, could not have been tested dynamically anywhere in the world, or in the future. We don't have machines to do that. But we could test reduced size isolators. And for that, one has to develop the theory. It's not just on the basis of opinion, but one has to develop isolators to be tested on the basis of theory that are concave or double friction pendulum isolators. This up almost 20 years ago. So you can see the use in these bearings of 2 sliding surfaces instead of 1, something that almost doubles the displacement capacity for the same size of isolator, but also very importantly, reduces the velocity of sliding between the top and bottom surfaces of the single sliding isolator. This is to 2, therefore reducing the heating effect. So you have 2 main advantages of these: the increase in the displacement capacity and the reduction in sliding velocity, and the reduction in heating effects, which are very important, as we are going to see. Now, the use of this articulation here is needed if you have friction coefficients on the two surfaces that are different, significantly different, not just minute differences. But if they are equal, then you don't need this articulation, and you can have a solid slider or pack in the middle. If you use different coefficients of friction, you may have additional advantages from this isolator. This is from testing on the shake table. We're going to call this later on qualification testing. This test was actually triaxial, including two horizontal and one vertical components of motion. I don't know if you heard a noise like bang, bang. That's because the isolator was momentarily uplifting. It wasn't visible, but it was separating. And from the measurements of force, it was clear that it was uplifting because the force, the shear force going through the bearing vanished. Going now to the triple friction pendulum isolator is simply a double friction pendulum isolator within another double, bigger double concave isolator. It has the advantages of the double plus adaptive behavior. As we move further and further away from the center, the isolator starts stiffening and resulting in a kind of a system to slow down for large displacements. We engage this in this stiffening behavior in extremely high seismic conditions to prevent collapse of the bearing. But as you are going to see in some applications, there is another advantage I will explain when we look at actual force displacement loops. This is one in the prototype testing for the San Francisco General Hospital, not long ago, I mean about 12 or 15 years ago. What I want you to look at the force displacement loops of these isolators. They show a behavior that is very similar to elastomeric isolators, except there is some very large effective yield displacement. So if you go and look at the unloading loop here, and from that estimate the yield displacement for this isolator is 60 millimeters, which is very large by comparison to a lead rubber isolator, is about 3 times larger. That has a beneficial effect on secondary systems. It's obtained by properly configuring these isolators, and that has benefits in a hospital where you reduce accelerations, particularly in the upper floors of the structure. Stiffening behavior, like in this case in the San Bernardino courthouse, prevents the structure from moving too much. You can realize that these displacements are in inches. So here we are at 1 meter. So this is approximately 1.1, 1.15 meters displacement. Here it is 1.1 meters displacement during this test. Now, looking at sliding isolators, like the friction pendulum we have seen, this is from the prototype testing of the bearings for that platform in Russia we've seen earlier. We see again the reduction of strength with the number of cycles, and this has to do with the heating of the isolators. And the temperatures are significant in the case of sliding isolators, more than actually in lead rubber isolators. And you can see the similar effects, I mean, of the reduction of strength in a lead rubber bearing and the reduction of strength in a friction pendulum isolator. This is very important to account for in analysis and design. We have models that can predict this analytically, this behavior. Quite complex, actually, and I will elaborate a little bit about that. But typically, these models are not used in practice in the analysis. Instead, we use procedures that determine upper and lower bounds of strength that are used in analyses with models that do not account for the changes in strength from cycle to cycle. For that bearing we've seen earlier for the hospital in Turkey, the Erzurum hospital, this theory I mentioned about, predicts actually quite well this is the energy dissipated per cycle, as well as the temperature increase in the lead core. And I wanted to show this here, that in this bearing, going over 3 cycles at the displacement for which the bearing was designed, the temperature increases by about 120 degrees Celsius, the temperature in the lead core. So if it were 20 degrees when it started, it is 140 after 3 cycles. Lead melts at about 320 degrees Celsius. There's a theory that predicts that very well, and solution to that can be utilized even by the profession. But key to that is the relationship between the effective yield strength of lead and temperature. It's a very simple relationship, and based on tests like this, and you can see the difference between 20 and 140 degrees Celsius, how the strength changes, but also the elongation at break of lead. So the bearing may start, the lead core may start breaking at high temperatures, but the good thing about it, when it cools down, it recrystallizes, so it basically returns to the original condition, even if it melts. We have a similar theory, of course, based on totally different concepts, for sliding bearings of how to predict the temperature rise at the interface, which controls now how friction changes with motion. And these graphs here show histories of temperature predicted and measured at some depth, not at the interface, because it's impossible to measure anything at the interface. And you can see these histories of temperature depend on how you move by comparison to the point at which you acquire the temperature. It's a kind of a complex theory to arrive at these results. But the theories have been codified in software like OpenSea. Some of you are familiar with that, which can be used by researchers, but also by people in the profession. An example of application of this in the profession is this analysis for the bearing. This is a triple friction pendulum for the Los Angeles County Museum of Art. This is a large isolator. You can see almost 3 meters in diameter, and was supposed to be tested, but it's impossible, at 3,000, this is 29,000 kilonewtons, so it's almost 3,000 tons at displacements of 750 millimeters dynamically for 10 cycles. But this could not be done. So analysis in this case predicted the temperature rise at the 2 main surfaces, and you can see it reaches about 200, 250 degrees Celsius. And then on the basis of this information, tests were designed for smaller bearings to emulate these temperature conditions, so that the isolator could be qualified for this test that could not be done. Now, going into testing, I mentioned about qualification testing that is conducted to qualify a new technology. It involves a lot of things, including the shake table testing we mentioned or showed earlier. We're supposed to observe behavior under extreme conditions, acquire data for use in model validation, but also in developing databases of properties to support analysis and design later on. Typically not done for a project, but for a product. And therefore, this is done with support from manufacturers as well as funding agencies. And this is images from tests done, just shake table test in our laboratory. And this is one similar to the one you've seen earlier, but this is more extreme now. So when we do testing, qualification testing, it's important to observe extreme conditions that not the conditions that are very easy to simulate. And in this particular case, there was very strong motion that engaged the restrainers of the bearings. You may have seen that during impact, the instruments that were light emitting diodes, there was a video system acquiring the data, they were knocked off the isolators. But very important in understanding behavior, you may have seen that the bearing recentered after the earthquake, despite the fact that it had these problems. Now, in terms of prototype testing that is done for each, we have seen a lead rubber bearing tested at this large machine at the University of California in San Diego. Is the largest machine available for testing isolators nowadays. So this is a prototype testing now for each project, 2 isolators in some types of structures, nuclear structures, for example. We're going to test 3 isolators of each type to acquire data to support the analysis and design. So from this data, we determine the properties, upper bound and lower bound, including other considerations. And it's very important to be done dynamically. In the United States, this is done typically under the supervision of the peer review panel. This is prototype testing that was actually much more complex. For a bridge in the United States, it's in the eastern United States, is the Woodrow Wilson Bridge in the Washington, D.C. area, in which testing of the isolators at the University of Buffalo, prototype testing included also wear testing, moving the bearings for a large cumulative travel, in this case 1,600 meters, to observe their behavior before and after this cumulative travel. So a testing like that may take weeks and months, so it's very time consuming. So in this video, we have seen testing of triple friction pendulum isolators for one of the projects I mentioned earlier in a machine of the manufacturer. This is prototype testing done under dynamic conditions. If they could not do the testing under dynamic conditions at the facility of the manufacturer, then the bearings should have been taken to a facility like the one we've seen at the University of California in San Diego for testing, or elsewhere. There are machines, for example, in Europe that can do this. Now, in terms of production testing now, this is a quality control issue. All isolators, at least in the United States, they are tested preferably under dynamic conditions. For sliding isolators, the friction pendulum type, all of them are tested dynamically, at least in the United States. It's very important to do this to reveal the properties of the isolators and meet criteria established in the design, as well as for detecting any problems the bearings may have. I don't want to go into details of the many cases in which problems were revealed in production testing, or isolators that failed because they were not prototype quality control tested. And it can be done. For example, on the project mentioned in this slide, this is a hospital complex in Istanbul, Turkey, in which there were 2,000 plus isolators that were all dynamically tested before shipment to the construction site. And this was only 5 years ago. So you can, This is from testing of a dumper, used in one of the hospitals, with dumpers in the state of California, is the Washington Hospital. In this case, it's only one cycle, but the velocity was 2.4 meters per second. Extremely difficult to do these things with a dumper like this that produces a peak force of 200 tons. Many structures in the United States use dumpers in the isolation system. This is a list of those. Most of them are hospitals, actually, and there is a reason for that. They are very close to active faults. And the other thing you may observe in this is the displacement capacity of the isolation system that increases as we go towards this one that just has been completed, in which the isolator displacement capacity exceeds 1 meter. And I will show a little bit more about that at the end of the presentation. It's the Loma Linda University University Hospital or Medical Center. It features a 3-dimensional isolation system that has not yet been installed. Only the horizontal one is now active.
Professor Costantino, sorry, we are slightly exceeding the time. So if, of course, we can allow more time, but just to let you know.
Okay, I think I'm finishing up. Just going through some of these images of examples of application in retrofit. Very important structures in the United States to be seismically retrofitted. This is much more difficult than a new construction because the structures are fragile, and not properly designed for seismic loads. And going through, this is the one of the largest structures to be seismically isolated, the headquarters of Apple. Apple isolator displacement capacity is 1.3 meters. Wanted to show one of, let's say, relatively tall structures of small footprint in Japan. You have problems with tension in isolators. Isolators in tension have very limited capacity and they fail under rather small forces. And this is, you can find information about this in these references of how they fail in tension. So elastomeric bearings in tension are typically avoided. And I will go over a case of the development of this 3-dimensional isolation system that is now used in the Loma Linda University Medical Center. This is from testing of a model for that. This was developed originally for large electrical equipment like transformers. You can see the challenge in 3D isolation because we have these problems with rocking, that can be control or reduce when you have large plant dimensions. In this case of this testing, the dimensions for this equipment are rather the plant dimensions small, so you end up with rocking, inevitable. But you realize that you have a horizontal isolation system and a vertical, rather stiff system that is highly damped. And you have to use springs in the vertical direction. You can see the significant effects of isolation in both horizontal and vertical directions. So the solid lines are the spectra at the shake table, and the dashed lines are the spectra, acceleration spectra at the control point, which is at the top of this tested structure. And you can see for the maximum accelerations, how much they were reduced, at least a factor of 2, but also everywhere else. Predictable, the behavior. The vertical displacements are small, as you can see about in this test, about 10 times less than the horizontal ones. And showing images from the construction of these first are schematics. These are my last slides. The isolation system for the Loma Linda University Hospital or Medical Center involves 126 friction pendulum isolators. These are triple. And you can see there are these large pedestals that are supported by spring units. There are about 1,000 of these spring units, and there are dampers in the vertical direction, about 1,000 of them. And there are these pins, about 500 of them, that drive the system in the vertical direction, the vertical isolation system in the vertical direction. There are also viscous dampers in the horizontal direction that will be seen in photographs next. One thing I wanted to emphasize here is the depth of the girder on top of the isolators. This is about almost a meter and a half, a little bit more in height. You need this to transfer the significant forces as the isolator deform to more than 1 meter. The dampers, you can see 6.5 meters in length. They have been installed, and you can see here, you can see the isolators. There's an isolator here. You can see a damper here. Another image that shows the girder above, the isolator, the pedestal. The pins will go here. You can see a pin installed. You can see the dampers here. Again, the girder on top. And as a final slide, I had some comments about this maturity of this technology and the benefits that they can provide, provided they are properly applied. And I'm ready to discuss some of these issues about what we still are struggling with, about multi-hazard considerations. For example, look at these structures in offshore structures, the procedures for analysis and design, accounting for lifetime behavior, and modeling actually the hardware to predict all those behaviors we discussed, as well as testing those giant bearings as we move to conditions that we cannot test. And with this, I finish my presentation. Thank you.
Thank
Thank you very much.
Thank you.
Sorry, Salvatore. Go
No,
ahead.
that's good.
No, I wanted to thank you, Professor Costantino, for this great presentation. It was very interesting. I was very sorry to stop you, but we have time constraint, and but there will be the discussion later, and I'm sure it will be super interesting. So now I'm happy to give the floor to the second presenter, Dr. Zhu, who is the Chief Structural Engineer of the Beijing Institute of Architectural Design. Among many projects, he's been responsible for the design of the active reflectors primary supporting structure of the 500-meter aperture spherical radio telescope. Also the FIFA World Cup Qatar 2022, the main venue of the stadium in Qatar, and of course the terminal building of the Beijing Daxing International Airport, which, as I mentioned before, was awarded as outstanding structure by IABSE in 2021. So now I give the floor to Dr. Zhu. Please, the floor is yours. Actually, it will not be Dr. Zhu who will present. Dr. Zhu is there, but his collaborator will practically present the presentation. Please.
Right. Okay. All right. Thank you, Maria. Hello, ladies and gentlemen. Thank you for your time to join this webinar, and thank you all the colleagues from the International Association for Bridge and Structural Engineer to arrange this webinar. Thanks to Professor Constantino. Your presentation is quite impressive. It is my honor to have this opportunity to present the seismic isolation design of Beijing Daxing International Airport terminal building. I am present for Dr. Zhu, who has limited speaking English, but he is here with me. And we are also from Beijing Institute of Architecture Design, based in Beijing, China. So I will share my screen right now. Can you see my screen now?
Yes, very well.
Yeah. Okay. All right. So just 1 second. Okay. The content of my presentation will be in 4 parts. The first one will be a brief introduction of the Beijing Daxing International Airport about the project. Second is a brief introduction of the structure system of this terminal building. And then a summary of the challenges during the design of this project. And finally is the main part, which is the seismic isolation design of for this terminal building, which is currently the largest seismic isolated building in the world. So I will start with the introduction. The total building area of this terminal and the transfer center is around 800,000 square meter. The projection area of the terminal building roof is about 270,000 square meters. The overall configuration is enclosed in a perfect circle with a diameter of 1,200 meters. The narrowest part of the central hall here is around 350 meters. So, and the airside corridors is about 400 meter long, 44 meter width, and 100 meter width in the end. The maximum elevation on the roof is about 49.5 meter at the center of the terminal building. The elevation of airside concourse varies from 19 meter to 24 meters. The terminal building is a pivotal transportation hub of Beijing City and Tianjin City and the Hebei province. It contains 2 intercity railway, which is high-speed railway with maximum speed of 350 kilometers, and 1 subway in the middle for the transport passengers between airport and to the city center of Beijing. So all the railway and subway platform are underground beneath the terminal building. There are a total of 7 stories, 2 underground here, and which is the transfer center for the railway and subway, and the rail station for level -2. There are 5 stories above the ground for the arrivals, departures, transfer, shopping, food and beverage, lounge, hotel, and so on. The overall roof has a projection of 350,000 square meter, and sorry, this is not projection roof. This is an area. It's not projected area, but an overall area. And it's a glass facade, has a area of 88,100 square meter. This is the render view of the main entrance and an interior view of the terminal. And there are 2 pedestrian linking bridge inside this building. And this is the interior view inside the main entrance. There are a couple of interior view for the C-shaped column, the skylight in the middle of the center hall, and the entrance facade. The C-shaped column here are the main support system of the roof of the entire building. Here are some photos taken during construction for the roof structure. This is a bird view of the terminal building during construction. This is a bird view when the terminal building is complete. Currently, it is the world's largest airport terminal, and it has been named as the top of the new seven wonder by the British Guardians. So next one is the structure system. The concrete structure has been divided into 19 segments. They are designed to be a frame structure, and the column grid is around 9 meter by 9 meter, 9 meter by 18 meter, and 18 meter by 18 meters. But we can see that for the center part, which will be the center hall, even with a dimension of 564 meter by 436 meter, there's no single joint at all, no expansion joint, no seismic joint, no settlement joint, no single joint at all. This is a roof structure. The roof structure has been divided into 6 segments. It is composed by the center hall and 5 airside concourse. The center hall are formed by spatial truss system. The maximum span is 180 meter. The maximum cantilever is 47 meters. The maximum structural height between the truss upper and lower chord is 8 meter. The roof structure type for the airside concourse is regular truss. So the architectural grace and appearance of the roof center creates an organic growth from the C-shaped column in the center hall. We have a small animation here. This C-shaped column forms the main support of the center core of the roof structure. Okay, so the central area is the most important part of the terminal building, and it is also the largest segment. The supporting structure of the center hall has 8 C-shaped columns in the middle, and 8 pair of supporting cores for each of the C-shaped columns. And there are curtain wall structure, facade supporting frame, and entrance column, and some single columns in the perimeter. We can see that there's no column in the middle, only in the C-shaped columns, which creates an almost a column-free space. If we look into more detail about the C-shaped column and the cores, we can further subdivide the roof into 6 typical units. Each one contain 1 or 2 C-shaped column and 2 supporting cores. The primary roof truss and that connecting the C-shaped column and cores, and the spatial truss between them forms this unit. So except the unit with C-shaped columns, there is also a center. There's also a center arch shield, right, supported by this unit in the middle of the terminal. This is a section here. We can see the relationship between the supporting core, the C-shaped column, and the center arch shield structure. This is a perspective view of the structural analysis model. So I will quickly summarize the design challenges that we faced in this project. So first one is for the roof. As we can see that from the structure system introduced before, the first challenge we face is the long span roof structure supported by the C-shaped columns. And the second one is the center hall, which has a planned dimension of 436 meter by 564 meter. It is large and full of architectural function, full of vertical transportations, and it is structurally quite complex, which makes the seismic resistance of this part much higher than the other part of the terminal building. It is required that this part of the building should be functional even when the maximum considered earthquake strikes. The third one is the vibration analysis and control for the terminal building with the real traffic fully integrated. I will skip this part. So here comes the main part. The seismic isolation design of the terminal building. I will introduce from 3 parts, which is why a new type of isolation system was proposed. And second is what is the component of this system. And the third one is how we design it. So first is why we introduce a new type of isolation system. So here are some existing seismic isolations. We have a roof isolation system, which has been applied in an airport in Turkey. It uses friction pendulum system to provide seismic isolation for its large span roof structure. And we have a base isolation. This was designed by us. It is the Kunming Airport Terminal. It is the first airport that's widely used base isolation system in China. And because this terminal is only 12 kilometers away from the fault zone in Yunnan province, the mass isolated for this project is 75,000 tons. This is a cross-layer based isolation. This has been applied in Haikou Airport in China as well. This is also designed by us, and the mass isolated for this project is 530,000 tons. So why the existing isolation system cannot be applied to this project, and why we introduce a new one? So the first one is that due to the complexity of structure system of the roof structure, the entire roof was not supported by a regular spaced columns, but by 8 C-shaped columns only. Even every column has to be seamlessly integrated into the roof structure, and the roof helps to improve the stability of these C-shaped columns, because C-shape is an open section, and it has a stability issue in different direction when the horizontal loading applies when earthquake happen. So that's why we can't use the roof isolated system. Second is the Beijing Daxing International Airport is a pivotal transportation hub. The high-speed railway and subway are fully implanted into this terminal. There are 3 lines under the terminal building. If the train does not have to stop, the maximum speed that the train passing the terminal will be 350 kilometers per hour, which is a very quick speed. The high-speed railway has extremely high requirement to the settlement of its foundation. And the bearings will also have horizontal deflections, which may affect the high-speed railway passing through. And that is why we can't use base isolation systems. So we have proposed a combination of base and interlayer seismic isolation system to this project to accommodate all the functions and function requirements. The yellow dashed line here is the isolation level, and the dark blue here, the dark blue part is the underground transfer center. The light blue one is the subway, and the purple color represents the highways, the high-speed railway platform. So the entire, so what second is what is the composition of the isolation system. The entire seismic isolation system is composed by 322 1.2 meter diameter leader rubber bearing, 510 1.2 diameter laminated nature rubber bearing, 82 1.3 diameter laminated nature bearings, and 93 1.5 meter laminated nature rubber bearing, and 111 sliding isolation bearings. The mass isolated above the system is over 1 million tons, which makes the system the largest isolated building in the world. In this 1 million tons isolated mass, the concrete structure takes about 94% of this, and the steel structure takes only 60%. And this also means that it is meaningless to use the roof isolation, as the roof only takes a very small portion of the overall weight of the building. So here are some photos of the rubber bearing and the sliding bearings during the construction. The bearing will be installed before the reinforcement concrete beams above it being constructed. The right one is the bearing with fire protection. In addition to the bearings, we have viscose damper, which large bearing capacity and long moving capacity are placed at the perimeter of the terminal building to control the overall movement under the maximum considered earthquake. It is a photo for the viscose damper taken during the construction. We can see that the damper were placed in both directions. The design life of the bearing are 50 years, and since there are viscose damper included in the system, the maintenance team of the building has managed to have a periodical inspection for the dampers. At the same time, the appearance of the building will be visually inspected as well. And if any abnormal is observed, the bearing can be replaced. These are photos taken during the construction. And regarding to the mechanical property and the durability of the bearings, the manufacturer of the bearing has invited a third party to conduct a test for the creep and aging. Conduct a test for the aging and creeping for the bearings. The bearings will be placed in a thermal tank and loaded to its design compression for 185 hours while maintaining 100 Celsius degree. This test is equivalent to a service life of 60 years for the bearing, and the bearing will be tested for their mechanical property before and after the test. And if the property varies is less than 25%, then the bearing product was considered to be reliable and can satisfy the 50-year design requirement. And to control the quality of all the bearings, according to the standard in China and the project specification, there are 3 types of tests should be fulfilled before the bearings could be installed on site. The first one is the prototype test. So once the bearing, if the bearing with new mechanical property and specification is developed, and a prototype should be manufactured and delivered to a government authorized third party to conduct the prototype test. And in this test, all the prototype will be tested and a report will be delivered by the third party. The test will include compression test, tension test, shear test, aging test, creeping test. The test will be conducted for the design load and all design situation, and also for the ultimate failure situation. Second one is the factory inspection. Before the bearing are packed and sent for delivery, all the bearings should be inspected and tested by an authorized third party inside the factory for their compression property and shear property under the design laws. The last one is the site acceptance. The bearing that delivered to site will be sample inspected by an authorized third party for about 3% sampling. The design approach of the seismic isolation system is following a brief flowchart on the right. Based on the design condition, like the site condition, the architecture function, we will first assume and structural performance target and decide what performance will the terminal building be during the earthquake. Then we can propose a seismic isolation system, and based on the type of this system to finalize a seismic reduction target. And it's mainly about a reduction factor of the layer shear force calculated when compared the analysis before the isolation and after the isolation. Normally, if the reduction of the shear force of the layer can reach 40%, then we can consider the seismic precautionary intensity to design this building can be reduced by 1 level. The vertical seismic effect should not be affected. Then we propose an isolation layout with combination of bearings and damper into a structure model. Run the model under the maximum considered earthquake and check the deformation, the tension, and compression. If everything passed the requirements, we can finish the design. So to ensure that.
Can you wrap up, because we are exceeding the time. We want to leave some time for the discussion. So if you can go to the conclusion.
Yeah, I will be very quick.
Okay, thank you.
Yeah, to ensure the bearing, we are not exceeding failure when maximum horizontal movement of the bearing appears during earthquake. And we have control the maximum of 12 megapascal for the rubber bearing and 25 megapascal for the sliding bearings for the maximum compression. And also the vertical stiffness of the bearing shall be carefully controlled to ensure the relative displacement between adjacent bearings. In this project, the maximum relative settlement is only 1/3,333. And we can see that from the table here that the analysis results illustrated that for the isolated model, shear force for all the levels has been reduced to less than 38% of the shear force in an unisolated model, which means that the overall seismic reduction of base shear is more than 62%. This is a time history and base shear curve, which also shows the result. And we can see that from this table here that this is for the steel structure. It shows that the shear force for steel structure has been reduced to less than 30% of the shear force in an unisolated model. This is also a significant reduction. We have controlled the interlayer drifting. The maximum for the concrete structure above the isolated layer is 1/322, and for the steel structure is 1/433 only. So based on this result, we can consider that the concrete structure will remain in a general elastic and the steel structure will remain fully elastic under the maximum considered earthquake. So this is the maximum. This is the interstory drift below the isolation level. The maximum interstory drift for level -1 is 1/1000, and in the x direction, and 1/984 in y direction. And also for the level -2 is much smaller. We have conducted a time history analysis for 7 earthquake waves. The maximum horizontal movement is 554 millimeter. And the base shear for X and Y input are listed above. And the base shear over gravity load of the building is around 10%. In addition to the seismic isolation, the system also helps to reduce the thermal stress from maximum 7.34 megapascal to 2.66 megapascal. The maximum reduction is 88%. So there was no crack observed on the slab since completion of the terminal. We can say that with this benefit from the isolation system, the terminal building realized a complete, a gigantic single concrete floor slab with area of 180,000 square meter, but with no expansion joint. It is a 1:60 scale shaking table test that was taken also to verify the design result. Excuse me. The results indicate that the seismic isolation system has achieved its predefined design target, and the isolation effect is outstanding. That's all. Thank you. Sorry for the exceeding of time.
Thank you. Thank you for both presentations. They're great. We have a few questions coming in the Q&A section of this webinar. We'll try to sort things out and ask some questions. We don't have too much time, but there is always an opportunity for you to answer the question later on. I think IABSE will provide the connection. So there's one for Professor Costantino. I think this was great to see, like a large-scale application, also like all the theory and the testing behind things. One question is about friction pendulum bearing, Professor Costantino, specifically about the friction pendulum bearing without rings. What do you think of that? Can you share something with you? And then still on friction pendulum bearing, like I try to combine the two questions, so for the sake of using our time most effectively. What do you think about uplift and the vertical impact when there is an impact between the two parts of the bearing, the friction pendulum bearing, after like an uplift type of effect? Can you try to answer this?
First, about the rings. I mean, in the case of the triple friction pendulum isolators, that's needed to get the stiffening behavior. But I don't know if you noticed in one of the slides I showed for the Los Angeles Museum of Art, LA County Museum of Art, there are no rings. But they are configured somehow, like if you look at that, to actually have that behavior. So there are some geometric considerations there that can do that, but is needed to obtain the stiffening behavior. Now, if I go to the double friction pendulum isolators, that are more kind of used because they are not, the patents expired or they don't exist anymore and they are more used. It's important to have these for a number of reasons. It's not to stop the structure from moving. You know, the structure is so strong, it's going to just, and heavy, it's going to slide through the ring like a knife through butter, you know. But they are needed because in case you install the isolator improperly and one surface has been contaminated and friction is much higher than the other surface, you are going to have sliding on the surface of the low friction, and then you are going to move and fall off because the displacement capacity has been reduced. So if you have a ring, you are going to be stopped, on the surface of least friction when you consume the displacement capacity and start moving on the other one, even with higher friction. But the displacement capacity is preserved at the expense of some abnormality in the loop, which is not critical. So it's important to have it. And I think in Europe, they are moving now to require that. It was a mistake not to have it, remove it, at least from the European specifications. Now, related to uplift, well, we have, just to give you an idea, for the Loma Linda University Medical Center you have seen, there are some isolators, very few that have uplift. And the uplift exceeds, let's say, is about 150 millimeters in some locations. And the bearing has to be configured to avoid that the internal parts disintegrate. Let's say you move too high up and you move over the internal slider and the whole thing becomes unstable. Now, the issue of coming back and impacting, you have to realize that you separate with the same velocity that you engage back. It's not going to fall from the sky unless the entire structure is in the air. Let's say when the vertical acceleration exceeds 1g. In the test, you may have heard that, and that had to do with the vertical acceleration exceeding 1g. Very important to include the vertical acceleration to properly predict shear forces, not necessarily displacements. But there are cases in which you can have a problem with uplift if you have only two bearing and the structure starts rocking like this, then you're going to have apparently impact, but we're not considering that. The other is that under certain conditions, because of the movement of the internal parts, there may be a gap that cannot, we have work done related to that, and in the references, since you're going to have the presentation, you can go and look at that, how that is predicted. It's exceptionally complicated, but one can predict that there may be a gap and there may be some, let's say, free fall, maybe 25 millimeters that these models can actually capture.
Okay.
Thank you.
Thank you. I'll try to summarize a few things in a question for both presenters. There's like a couple of questions around the issue of modeling, what type of software you use to model the seismic isolator in your application. I see from like my observation of your presentation, there is a lot of complexity deriving like also from the input that is used, and especially the combination of vertical movement with lateral movement and all the stuff. It seems that you've been using just, maybe a few words about your approach to relating the analytical analysis, the model to also to like measurement in the field. What you actually see in the behavior of the structures, and also how do you relate your analysis to like when you do testing on a scale model instead of full model? It's kind of like a very broad question, but it's more like say a little bit more about how you analyze, especially for the airport, how do you analyze the system, how many different cases you have to do for like an accelerometer and all the stuff. If Zhu can try to answer this question, maybe you'll give it.
Dr. Zhu, can you hear us? Maybe there is some problem of connection now. Well, there are
They
plenty
are
of questions
muted.
for
You can unmute them maybe.
but I suspect they cannot hear me because they are not answering. Well, maybe we can go on. There is plenty of. Oh, okay,
Go ahead.
okay.
Yeah,
thank you.
sorry. There's an internet problem. There's a connection problem. I only can you repeat the question again?
It's more like if we kind of say, summarize a little bit more your approach to modeling, what type of software was used and what type of like input for the analysis of the seismic event you've been using for that such a large scale project.
Right. So the software that we use for design this project is the Midas GN general structure analysis software, and also we are using IABSE, and there's also our company have developed and structural analysis software as well. We use 3 of them for the design, and we use SAP 2000 for validation of the analysis result.
And then in terms of like seismic input, earthquake, you use accelerometer recorded at the site. You have a probabilistic approach to that. Can you say something about that?
Yeah, we use we are based on time history analysis and also spectrum analysis as well. For the seismic analysis, for the time history analysis, we will find some earthquake waves and with similar spectrum property to the site condition, and we use that we amplify that to its design precautionary intensity, and we just input the ground accelerometer into the software. And
Did you consider the spatial variability of the input or not? This was another question.
Sorry. Say
Did
again,
you
please.
consider the spatial, since it's a large structure?
Yeah.
Did you consider the spatial variability of the ground motion, or it was just a uniform input?
We consider that as well.
Okay,
not
good.
only uniform input. Yeah.
There is Salvatore, do you want to go ahead with another question to Professor Costantino, maybe?
One thing is, for Professor Costantino, this is more coming from me. What do you see, the advancement in the field of base isolation? I see a lot of like more complexity of combining different type of isolators together, the size of the project, but also in terms of like materials and like evolution of stuff, things that we can see more used in the future compared to what we have seen so far.
Well, I don't believe there is much to invent. Well, there are a lot of people inventing things that are have been already invented. I mean, as editor of a journal, I reject, say, about 65% of papers submitted without review on the basis that they do not contribute anything, and most of them are innovations to things like this. So there are people who come up with ideas that are not necessarily meaningful. We have already pretty good technologies. We have rubber bearings, we have sliding isolators. Soon these sliding isolator patterns will expire and everybody will be making them. So there are going to be many companies quite good, capable of making this. And the issues here is to make them with materials that have the longevity and the reliability expected of them. The other is to make predictions. For example, we heard about 50 years of lifetime for isolators for the airport in Beijing, which is typically what we consider. The question is, how do we know that it's going to last 50 years, right? Can we run a test today that will predict that? I will challenge anybody on the basis of scientific considerations, not opinion, principles of physics, that in chemistry, that will give me that information. We talk about accelerated aging and things like this, nothing of which can be scientifically defended. And I'm really strong opinion, I have strong opinion about this. And that evolved also in the offshore platforms in Russia. We went through almost 15 years of review, not 15 days, 15 years of review by a panel of Russian scientists who were physicists, not engineers. And without this cloud of science around it, you could not have received a permission to build those things. So these are very important issues indeed. I believe longevity, reliability of the site, prediction of the lifetime behavior and things like this. We have a good understanding, I believe. And I believe a rubber isolator properly made will last 50 years with very few changes. But most of it is based on the limited information we have so far. So well made, however, properly cured. We have problems with that, however, they would last certainly 50 years, maybe more. Now, there are other issues related to models for analysis and things like this and all the stuff. Those are advancing, you know, and we will soon be more readily available to the profession. Some companies, for example, to give you an idea, a company like IABSE is develop their own, elements and things like this in LS-DYNA, quite sophisticated, that they use, you know, but they will be available in softwares like OpenSeas that the profession doesn't use. Eventually, they will be implemented in SAP 2000 and ETABS that the profession can use. There are options to use in software like ANSYS and Abacus, but they are too complicated. For example, you can model spherical surfaces of sliding, but if you have 1,000 isolators, it's going to be very difficult. Or in the hospital in Turkey, the one I've shown, there are 2,000 isolators. So this is a single, this is the I wanted to make that comment. The hospital I mentioned just 5 years ago was designed by Arab, actually, or Arab was one of the participants in that. It's actually 2,000 isolators in a single surface, that they isolate. So it's more than the airport in Turkey, in China from that 2,000 isolators carrying about the same load, however, not more load. But I wanted to make a comment if related to what the presentation of Dr. Zhu or his engineer mentioned about the isolation of the roof, and the example was the airport in Turkey. That's not a correct statement. That was an isolation of the roof, because I was involved in that, and I'm the one who was responsible for that. That was a structure that was upgraded, retrofitted to a certain extent after the earthquake of '99 when it was under construction. Because of this problem with expansion joints that is required in the Turkish standards, every 50 meters to have an expansion joint. There were columns that were a quarter and half columns. So instead of being 800 by 800 millimeters, there were areas in which the columns were 400 by 800 or 400 by 400 millimeters, not resisting much load. And they had to be designed to remain essentially elastic when the original design was used an R factor of 7, by the way, incorrect. So the joints were fused, the columns were jacketed, concrete and steel, concrete and then a steel jacket to the size of almost 1.2 meters in diameter. But still the force transmitted to the top floor, which was the departure level, was too high, and one had to reduce the force transmitted from the lightweight roof to the top floor columns, and only isolation can do that. We could have had the columns larger, but the architect refused to allow more than 1.2 meters diameter columns. And that was the reason isolation was used. Is not
I think
isolation system, is a system to limit the transmission of force just to the third story columns, not the rest of the building. So it's not an isolation, and it's not an example of isolation. It's an example of something else.
I don't know if Dr. Zhu wants to reply, but anyway, there is another question for Dr. Zhu, which is a curiosity. Why you didn't consider FPS for the isolation of the airport, and also a more basic question, which is, since the structure is very flexible, the period is higher than 1 second. Why did you consider isolation? There is also this other question. So why isolation for a flexible structure, and why not FPS? And then if you, of course, if you want to comment on the comment of Professor Constantine.
Right, okay, so I will try to answer the first question is why we didn't use FPS. Because the terminal building was the design of terminal building was completed in 2015, and at that time there is no much FPS application in China, not yet in Chinese project, but rubber bearings are widely used, and they have a lot of test result and good application examples. So this is the main reason for not using FPS, because we want to use a reliable product here for this kind of important building. The second one, for why we use isolation system for a structure with a period of 1.27 seconds is we have extended that the period of the structure to 3 seconds, and we have a significant reduction of the seismic effect. And also, there is another important reason why we use seismic isolation, is that the seismic isolation system not only helps to reduce the seismic effect, but it also reduces the thermal effect on the concrete slab, because there is a requirement for the terminal building that for the central area, which is almost 500 by 500 meter large, and for that area, we should not consider any expansion joint. So the seismic system reduce the thermal stress under both temperature affection and also the creep and the shrinkage of the concrete slab to a quite small level, which makes it possible. And this is also another important reason why we use seismic isolation system for this terminal building. Thank you. Thank you very much.
I hear an echo now. We are 10 minutes beyond the schedule. Maybe I would, with regret, I would close the webinar. I'm sure IABSE can send you, IABSE Secretariat can send you the several questions that are in the Q&A. And it would be great if you could answer the participants. But before closing, finally, I would like to share again my screen. Because, can you see my screen? Yes, I guess so. As I mentioned before, IABSE has several task groups, and one of them is focused on improving seismic resilience of reinforced concrete structures, which is a quite numerous group. Here you can see a picture. The chair is Andreas Lampropoulos. And I'm mentioning this because the next IABSE webinar will be again about seismic isolation and response control systems. Recently, a document, the IABSE said a document has been published. And in this webinar is based on the document. It will be described by 4 speakers that you can see here. And I hope, I'm sure, many of you will be interested in this event. So save the date, will be the 17th of June at the same time as this one at 2 p.m. In the afternoon. Okay. And with this, I think, well, I really want to thank the two speakers, Professor Costantino and Dr. Zhu. It was a very, very interesting event, and this is shown also by the large number of questions that we were not able to ask the speaker for time reasons. And I thank you all the participants, of course, and I leave the word to Salvatore that maybe wants to say something as well.
No, I think it was a great presentation. We learned a lot, and I think there was also a good lively exchange of question and answer. We're always limited with time. We are like more than 130 participants, and again, I want to thank them for the attention, and keep your eyes on the IABSE communication for future events of this type. Thank you very much.
Thank you. Bye. Bye.